I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. We currently are discussing the case of cointegration in time series econometrics. So, cointegration, if we want to define it, then we can say that two variables will be cointegrated if they have a long-term or equilibrium relationship between them. Till now, we are done with the Engel-Granger process of Johansson cointegration. A quick recap of it. And therein, what the case was that if two series, yt and xt, they share a similar stochastic trend, and the difference of them, that is et, is stationary, then we assume that they will not diverge too far from each other. So if we go for a non-stationary time series and we go for estimation of their parameters by using OLS, then we may get spurious results. So then we need to check for the stationarity of the series. So if both the series are I1, that is integrated at the first order, then according to the rules of an integrated series, any combination of them, that is et hat is equal to yt minus beta 1 minus beta 2 xt, this linear combination of two integrated series, it should also be I1 integrated at first order. But as a special case, if this linear combination or if the series of et hat is I0, then we can say that these two series are cointegrated. So basically in Engel-Granger process, we were testing for the stationarity of the residuals. If the residuals are stationary, there is cointegration. If the residuals are not stationary, then there is no cointegration between them. So the process was the same, that we do that et hat and we calculate this et hat, we check, we estimate et hat, and then we use an augmented Dickey-Fuller test and we get the result. If this et hat is stationary, then we say that there is a cointegrating relationship between them. Next, when we were discussing Engel-Granger process, we have come across few limitations of this process. One of them is, this is not generally, you cannot say that this is only the limitation of an Engel-Granger cointegration process, but if you go for the other methods also, then this cointegration or the presence of an cointegration is only a necessary condition. Because if yt and xt are cointegrated, it does not mean that they will move like a straight line, like a parallel track of railway. They may have some other shape with some short-run deviations. And if they are tied in the long run, these short-run deviations need to be corrected. If only they are correcting, then only we can say that this long-run relationship will be maintained, or else they will diverge, these two series will diverge from each other. In this Engel-Granger process, or in the process of cointegration itself, we are not aware whether xt is adjusting to yt or yt is adjusting to xt. For this, we have to reformulate the model as error correction model. And if it is a multi-equation framework, then we go for vector error correction model. But now at the moment, it is just a single equation framework we are discussing. So we will see how, what is this error correction model. See, cointegration refers to a statistical property of time series variable. When two or more series are cointegrated, it means they share a long-term trend. This long-term relationship between the variables implies that the variables move together in the long run, even if they deviate from each other in the short run. So this error correction model is a crucial component in models involving cointegration. In a cointegrated system, there exists an equilibrium relationship between the variables. However, in the short run, deviations may occur from this equilibrium due to the shocks or any other temporary factors. Now, the ECT, or this error correction term, which we get through this error correction model, it captures the speed of adjustment back to the equilibrium relationship when such a deviation occurs. So the basic idea is that if the variables are cointegrated, there should be an error correction mechanism at play. This means that if the variables deviate from their long run equilibrium relationship, there will be adjustments that bring them back to the equilibrium relationship over time. This error correction term captures the short run dynamics of this adjustment process. Say if xt, what we have, we estimate a long run relationship by regressing yt on xt, and we get yt is equal to theta 1 plus theta 2 plus xt. We get theta 1 plus theta 2 xt plus epsilon t, where theta 1 and theta 2 are the long run coefficient. But we are also interested in estimating the short run behavior. This is achieved by this error correction model. And for this, we use what we call as Granger representation theorem. This theorem states that if x and y are cointegrated, then the relationship between these two variables can be represented by an error correction model. In practical terms, models like this error correction are used to analyze the cointegrated time series data. This ECM includes lagged values of the variables and the ECT itself, and by estimating such a model, researchers can analyze both the short run and long run dynamics of the equilibrium relationship between variables. And according to this Granger representation theorem, if xt and yt are cointegrated, then the relationship between x and y can be represented by an error correction model. So to explain the process, we take an ARDL model. An ARDL model is an autoregressive distributed lag model, which implies that yt is the dependent variable and it is also present as an explanatory variable in the lag term. Plus, you have the independent variable and there can be lags of the independent variable also present in the system. That is why we refer to it as autoregressive distributed lag models. Now, in order to ascertain this long run relationship, if there is a long run relationship, then what we have, yt is equal to yt minus 1 is equal to yt. And also we can say that xt is also equal to xt minus 1 is equal to x. We will use the denotation, we will use the symbols of y and x. So we replace, that is, if there is a long run relationship and also if the data is now stationary, what we can say that yt is equal to yt minus 1 is equal to y and xt is equal to xt minus 1 and also is equal to x. So we replace yt by y, yt minus 1 by y, xt as simply x and xt minus 1 as also x, and each of them are having a coefficient term. So y is equal to sigma plus theta 1 y plus theta naught x plus theta 1 x plus sigma, excuse me. So y is equal to sigma plus theta 1 y plus sigma 0 x plus sigma 1 x plus vt, the error term. Now, here next time, at the moment we assume vt is equal to 0. So what we can do, we can take this y term over to the left hand side And we have y minus theta 1 y is equal to sigma plus sigma naught x plus sigma 1 y. Now we take 1 minus theta 1 common, so we can write 1 minus theta 1 the whole multiplied by y is equal to sigma. Now here also there is x, and in the next term also there is x. So what we write, it is sigma plus, we take common sigma 0 plus sigma 1. This, please note this correction, this one should be inside. Sigma naught plus sigma 1 the whole multiplied by x. So now we take this 1 minus theta 1 to the right hand side in the denominator. So y is equal to sigma divided by 1 minus theta 1 plus sigma naught plus sigma 1 divided by again 1 minus theta 1 multiplied by x. Now we can just assume that this term sigma divided by 1 minus theta 1 as b1 beta 1 and sigma naught plus sigma 1 divided by 1 minus sigma 1 as beta 2 multiplied by x. So we are denoting beta 1 by this term, we are denoting beta 2 by this term. Now we again consider our the ARDL model which we had started with, that is y is equal to sigma plus theta 1 yt minus 1 plus sigma 0 xt plus sigma 1 xt minus 1 plus vt. Now we do some algebraic manipulation, that is we add minus yt minus 1 to both the right hand and the left hand side. So we have added this term in minus yt minus 1 to the left hand side and also to the right hand side. We do another manipulation therein. To the right hand side of the equation we add one term sigma naught xt minus 1 and we also deduct it by the same term, that is sigma naught xt minus 1 in the right hand side. So we have the sigma naught xt minus 1 as with a plus sign and also sigma naught xt minus 1 as a negative sign. So our full equation becomes delta yt is equal to sigma plus theta 1 yt minus 1 minus yt minus 1 plus sigma naught xt plus this addition term plus sigma 1 xt minus 1 and minus sigma naught xt minus 1 plus sigma naught xt minus 1 plus vt. We do another algebraic manipulation, that is we add a term sigma naught xt minus 1 and also deduct by the same term, we take minus sigma naught xt minus 1 to the right hand side. So what we do, we have in our this equation we incorporate minus sigma naught xt minus 1 and as a minus with a minus sign and sigma naught xt minus 1 with a plus sign. So our final equation becomes delta yt is equal to sigma plus theta 1 yt minus 1 minus yt minus 1 plus sigma naught xt plus sigma 1 xt minus 1. These terms are what we have just before, and we add these two terms, one with the same terms, once with a minus sign and next time with a positive sign. So delta yt is equal to sigma plus, now what we do, we take here yt minus 1 and yt minus 1 is common. So we can write sigma plus theta 1 minus 1 multiplied by the whole multiplied by yt minus 1 plus again here also sigma naught and sigma naught over here, sigma naught xt, and we have sigma naught xt minus 1. These two terms have the same coefficient sigma naught. So we take sigma naught common and what is left is xt, and here it is minus xt minus 1. So we get this term sigma naught multiplied by xt minus 1. Then we have two terms left, and here also there is xt minus 1, here also there is xt minus 1. So we take xt minus 1 as common, and sigma 1 from here and sigma naught from here, we take it as a bracket and within bracket and multiply it with xt minus 1. So we get this equation wherein we have taken once sigma naught common, another time xt minus 1 common, and in the first term yt minus 1 as common. So now what we get the equation as delta yt is equal to sigma plus theta 1 minus 1 multiplied by yt minus 1 plus sigma naught delta xt, because this is what, if you see xt minus 1, this can be written as delta xt, and next time we have in bracket sigma naught plus sigma 1 multiplied by xt minus 1 plus vt. We take one, then we can write it as this sigma, this term sigma plus theta 1 minus 1 multiplied by yt minus 1, and this term, the second last term, as sigma 0 plus sigma 1 multiplied by xt minus 1, and this term sigma naught xt we write it at a later time plus vt. The purpose for this is to write this equation as in this final format. Now herein what we are writing it as a final format is theta 1 minus 1 multiplied by, we are taking this term sigma also within the bracket, so we divide it. So what happens when we divide? So basically it is theta minus 1 multiplied by sigma divided by theta minus 1. So this theta minus 1 will be cancelled. So we can write it as theta minus 1 multiplied by within brackets sigma upon theta minus 1, plus since we have taken theta 1 minus 1 outside the bracket, so what is left from here? Only yt minus 1, and here then from here we can write sigma naught plus sigma 1 divided by theta 1 minus 1 multiplied by xt minus 1, plus you have sigma naught delta xt plus vt. So we can write this equation in this format. Now what we are doing, we are assuming this term, the same equation which we had derived in our previous slide is written over here. We are assuming theta minus 1 to be alpha. So alpha is equal to, we can write it as, we can write it using, we can do just a small manipulation. So we can write theta is equal to 1 minus theta. Why? Because say minus alpha is equal to, if I take it as minus alpha minus 1 minus theta, because in this term we can say, we can denote it by minus, so we have got a minus sign over here. When we open the bracket, this minus sign goes inside, so it becomes theta minus 1, it becomes theta minus 1 is equal to alpha. So now what we have left is theta minus 1 is equal to alpha. So minus alpha will be equal to, we can say it the other way, that is 1 minus theta. So once we have defined this, then we can write the next equation in terms with a minus sign over here, minus alpha multiplied by within brackets sigma divided by sigma theta 1 minus 1 plus yt minus 1 plus sigma naught plus sigma 1 divided by theta minus 1 xt minus 1 plus sigma naught delta xt plus vt. Now this term, that is sigma divided by theta 1 minus 1, we know we can write it as sigma upon 1 minus theta, and this term sigma naught plus sigma 1 divided by 1 minus sigma 1, we have denoted it by beta 2. We have done this before. So now we can write this equation in this format. So delta yt is equal to minus alpha bracket open yt minus 1 minus beta 1 minus beta 2 xt minus 1 plus lambda sigma naught delta xt plus vt. This term is just the same. It has been repeated twice. So this is what you define as your error correction model. So error correction model finally turns out to be delta yt is equal to minus alpha bracket open yt minus 1 minus beta 1 minus beta 2 xt minus 1 bracket closed plus sigma naught delta xt plus vt. We just write the equation again. This is the cointegrating relationship as presented in an ARDL model. Here alpha is equal to 1 minus theta. So minus alpha is equal to minus 1 minus theta, which we can write it as theta minus 1. So this alpha, this gives the speed of the error correction term. That is, how quickly the disequilibrium is corrected. If yt is greater than beta 1 plus beta 2 xt in the previous period, then yt decreases and delta y is negative. So if it is yt is greater in the previous period, then in the next time it will decrease, so it will return back to the equilibrium. Hence the error, whichever the short run deviation is corrected. So basically, error correction model is a reparameterization of the ARDL model. This model incorporates both the long run relationship between y and x and also the short run dynamics, and that is, it gives the proportion of error that is corrected in each time period. Now, it also shows that we can work with I1 variables, that is variables which are stationary at first difference, and I0 term, that is yt minus 1 minus beta naught minus beta 1 xt minus 1 in the same equation. So we have taken yt minus 1 and xt minus 1 and this term, provided that if these two series x and y are cointegrated, meaning thereby these terms, that is yt minus 1 minus beta naught minus beta 1 xt minus 1, it contains the stationary residuals. So, a dynamic relationship between I1 variables, which include a cointegrating relationship, is known as the error correction model. It allows for the existence of an underlying or a foundational link between variables, that is a long run relationship, as well as the short run adjustment, that is changes between variables, which leads to adjustment towards the cointegrating relationship. And now to estimate this delta yt is equal to minus alpha yt minus 1 in the bracket, to estimate this delta yt is equal to minus alpha within brackets yt minus 1 minus b naught minus beta 2 xt minus 1 plus sigma 0 delta xt plus vt, we can use our ordinary least squares method. So we get, when we estimate this model, we can retrieve the parameters as, we estimate this model beta 1 asterisk plus alpha asterisk yt minus 1 plus minus beta 2 asterisk xt minus 1 plus sigma naught delta xt minus 1 plus vt. So when we retrieve the parameters, alpha is equal to minus alpha asterisk, beta 1 is equal to minus beta 1 divided by alpha asterisk, minus beta 1 asterisk divided by alpha asterisk, and beta 1 is equal to minus this is again a repetition. So beta 1 is equal to minus beta 1 asterisk divided by alpha asterisk. To estimate this error correction model, we assumed a single equation framework. So if epsilon t is taking place in both y and x, we have to consider more than two equations. So if two variables, then two equations, then we need to estimate vector error correction model where we have a multiple equation framework. Now, see this term, and again an explanation of the things, that is this term yt minus 1 minus beta 1 minus beta 2 xt minus 1. It shows the deviation of yt from the long run value, and beta 1 plus beta 2 xt minus 1 is the error from the previous period. So theta minus 1 or minus alpha, it shows the correction of delta yt to the error. If the error in the previous period is positive, that is yt minus 1 is greater than beta 1 plus beta 2 xt minus 1, then yt should fall and this change in yt should be negative and vice versa. So this is the basic mechanism of error correction model. So if a cointegrating relationship, I am concluding it with, if a cointegrating relationship between y and x exists so that the adjustment always work, then error correct, then empirically we should also find 1 minus theta 1, it should be greater than 0, which implies that theta 1 is less than 1. And if there is no evidence of cointegration between the variables, then the estimate of theta 1 would be insignificant. I hope this discussion of error correction term is clear to you. So the basic things which we get from here is that this error correction term, it should be negative. If only it is negative, it implies that if there is a deviation, it will revert back. So the first condition as such is the error correction term, it should be negative. And the second, so your error correction term, condition 1 is it should be negative, and the second condition is it should be significant. And the third condition is that this error correction term, it should be less than 1. So these are the three conditions which will then only we can say that there exists an cointegrating relationship or a long run relationship between xt and yt or any two or more than two series. There is a cointegrating or a long run relationship only when the error correction term is negative, is significant and is less than 1. This is basically the sufficient condition. After this, we can safely say, now we need to check for the other things, because we are estimating it through OLS. We need to check for head serial correlation and heteroscedasticity. If all these residual diagnostics are fine, then we can safely say that xt and yt are cointegrated. They are moving together in a long run, and even if there is some disturbance or deviation in the short run, it will be corrected to the tune of this error correction term in each time period. Hope this discussion on error correction term is clear to you. Thank you.